Good morning to you all. So today we will be having the session 4 and we will be discussing about the orbital mechanics. So what is an orbital mechanics? Where a satellite is being launched in an orbit. So how it stays in the orbit is what we are going to see. So these are the basics of network law. Force is equal to ma. Force is equal to mass into acceleration is the most important law that will be applicable for orbital mechanics, for satellite to remain in an orbit. Okay, so we are going to see in the coming slides how this formula will be used so that the satellite remains in the orbit. So why do satellite keep moving and stay in an orbit? That one question that may be asked, that why satellite keeps on moving, why it's not going away, why it's not falling towards the earth. So there has to be one force that is actually happening on the satellite which are opposite to each other, so that both the forces are cancelling each other, and hence the satellite remains in that orbit. So if a force is applied in such a way that all forces cancel, the body becomes somewhat at a particular place, it will remain in that orbit. That is what our intention is. So here you can see the centrifugal force is there because it is moving in the elliptical one, and one will be the gravitational force. The earth attraction would be there. So both will be opposite of each other, cancelling each other, and then since it is cancelling each other, basically the satellite will remain in that elliptical orbit that is shown in the diagram. Force is equal to mass into acceleration. So this formula will come into picture. We will see how the units is being mentioned. So here if you see, the acceleration due to gravity is given by a formula nu upon r square kilometer per second square. R is the radius of the earth and nu is the universal gravitational constant. Basically it is the gravitational constant g multiplied by mass of the earth. So both are constant g and me. So by multiplying we call it as a nu, and the value comes out to be 3.9 into 10 to the power 5 kilometer cube per second square, and the value of g is 6.67 into 10 to the power minus 11 Newton meter square per kg square. So here you can see the both forces are, as I mentioned, are opposite to each other and they cancel each other, so that there is no drift in the satellite and it remains in the orbit. So what we are going to do is we are going to equate these two. So just now I told you the acceleration formula is nu upon r square. So force is equal to ma. We are putting the formula nu upon r square in the acceleration is equal to mass into gme upon r square. So that is your centrifugal force. So both ma and centrifugal force are being compared or have been made equal. So here acceleration again is being used for v square by r. So now if we go by here, if we equate mv square upon r is equal to mgme upon r square, we get orbital velocity is equal to nu upon r. Now this is a very important equation, and where we learn that the orbital velocity does not depend on the satellite mass. It does not depend on the earth mass. It only, because nu is constant, nu is g into me. So basically nu is a constant. So orbital velocity only depends on the distance from the earth surface, satellite distance from the earth surface. So here if you calculate the orbital period, if you put it, so it will come out to be 2 pi r cube up r 3 by 2 upon nu 1 by 2. So any orbital period can be calculated by this formula. Again, if you observe, the orbital period also depends only on the distance, because this is only the variable, nu is the constant. So as the distance r increases, the satellite moves with a lower velocity and shall have the higher orbital period. So basically as the distance r increases, satellite moves with lower velocity. So you can say the GEO moves with lower velocity as compared to LEO, because GEO is farther, it is 36,000 kilometer away, whereas LEO is 500 kilometer away. So LEO will be moving with a higher velocity and GO will be moving with a lower velocity. So these are the orbital velocities and periods for various satellite system: Intelsat, EcoGlobal, Skybridge, Iridium. So this is the orbital height. So you can clearly see Intelsat is the height of geostationary, EcoGlobal in the height of MEO. Okay, these are the orbital velocity. So higher the distance, lesser is the orbital velocity, and these are the orbital period. So clearly you can see the geostationary orbit is having a very close time period of Earth, that is 24 hours. Okay, little bit of variation is there. So once, as I mentioned, that in geostationary time period, a satellite launched in the geostationary orbit will have a orbital period of same as that of a Earth, that is 24 hours. Now this is the law that is going to be playing very important law, that is being given by Kepler's law. So let us see the first law of Kepler's law. All the planes that move around the sun in elliptical orbit with sun at one end of the foci. So basically here we are talking that if any object is moving in an elliptical orbit, then the sun will be in the foci. So this is ellipse. So ellipse will have two foci. One will be here, another one will be here. So any object that is moving in an elliptical orbit, say a satellite around the sun, then if you know that elliptical orbit, then the location of that sun will be in one of the foci, either of the one. So there will be two foci for ellipse. So either it will be situated here or it will be situated here. Now you want to be surprised that why we have used sun here. In case of the same diagram, you can put here as a Earth, and this you can assume it to be satellite. So basically the same diagram is applicable for Earth and satellite also. Okay, and remember, this is the major axis and this will be the minor axis. So this is the first law, that all planes move around the sun in an elliptical orbit with the sun at one of the foci. So if the orbit is given to you and you have been asked locate the Earth or the sun, then you choose any of the foci, that will be your correct answer. Now let us come to the second law. A planet sweeps out equal areas in equal intervals of time. So basically, see, as you know that satellite moves in an orbit at a different speed if the orbits are different. Okay, so given time period is same, then obviously distance travel will be different. This satellite has moved only to this distance, this satellite has moved to higher distance. Now this law says that the area swept will be same. So if you calculate the area of this particular region and compare with this, they will come out to be equal. The reason, because both have the same time interval. So this actually this is the one of the characteristics of an ellipse. So if the time period is same, then the area swept will also be same. So this is your second law of Kepler's. Now let us come to the third law. The third law says that the square of the orbital period of a planet is proportional to the cube of the orbit's semi-major axis. So what is a semi-major axis? From here to here. This is major axis and semi will be half. So this will be semi-major. So A is the semi-major. This is B is the semi-minor. So here they are talking about semi-major. What is the third law saying? The third law is saying that the T square orbital period, square of the orbital period will be proportional to cube of the orbit, semi-major axis. So these are the 3 laws of Kepler's that can be applied to a satellite or a planetary body moving around the sun, or any particular orbit which is having a elliptical orbit. So this is the only topics that we have for this session. I hope you have enjoyed the class. Thank you.